So let's start. I'm Andrianna Polydouri, and we're going to talk about Superlight blockchain clients under Velvet fork deployment method. And let's start with some preliminaries because this work needs some background. Now, I guess you've all heard about the SPV Light Client Protocol introduced in the Bitcoin white paper. So we have a light client protocol that says, well, in order for the clients to be more efficient, they can only download and process the block header information from the blockchain and not the whole blockchain information. And they can verify the proof of work contained in each blockchain and synchronize to the longest valid one, the one having the most proof of work in it. So this is an efficient protocol compared to having to download the whole blockchain, but it's not efficient enough because this means that the client should download data that grows linearly to the size of the chain. And what we will be talking about is Superlight clients, where we have protocols that require the clients to process only a logarithmic amount of data in respect to the size of the chain. And we will see two such protocols, the Superblock Nipopause and the Fly client. So let's first talk a bit about the Superblock Nipopause protocol. As you know, all valid blocks in a chain should satisfy the proof of work equation, meaning that the hash of the block should be less or equal to a certain threshold value t. And the interesting thing is that because of the way that the blocks are generated and because of the proof of work puzzle itself, the hashes of the blocks in a chain are, the values of these hashes are distributed uniformly within the range, the accepted range of 0 and this threshold value t. So we expect to see blocks that has to values much lower than this threshold value t. And these are rare blocks that also are expected to be seen in the chain in a regular fashion. So the Superblock Nipopause protocol counts on these luckier blocks, which we will call superblocks, in order to make the client synchronization a much more efficient procedure. And for this example toy chain, let's say, we have draw the blocks in the chain. Well, the taller ones are the luckier ones. So you can see that if we say that we want to convince a client for the proof of work contained in this chain, we could just send these few blocks that are at least of level 2, meaning these 4 blocks you see over the red line. And this should be enough to convince the client for the cumulative proof of work contained in all of the 16 blocks in the chain. So we are able with this protocol to construct really succinct proof for the client synchronization. Now, the thing is that this protocol, in order to function securely, it needs to make some consensus protocol changes. And what we have here is that apart from the previous ID pointers included in each block header, we also need to add some extra pointers, and these pointers are what we are going to call super pointers, and are the pointers that point right from one super block to the most recent generated one, previous one. So we are talking about extra pointers in the block header and consensus protocol changes. So we have to discuss about a method of deployment of these protocol changes. Which brings us to a discussion about hard fork, soft fork, and later velvet fork. So I guess we've heard about hard forks and soft forks, and so I'll be really fast at this. Hard fork is not backwards compatible, and it comes with the fact that on the one hand, unupgraded parties would not accept upgraded blocks because they stand for different protocol rules. And upgraded parties also do not accept unupgraded blocks because they don't satisfy the new protocol, consensus protocol rules. And this is generally believed to be quite a dangerous way to implement protocol changes because it may lead to permanent fork of the network. And then we have the soft fork, which is backwards compatible, meaning that the protocol changes that need to be introduced are added as auxiliary data, let's say, in the Coinbase transaction. And this means that the unupgraded parties could not distinguish the upgraded blocks because they pass the new information merely as comments. So they accept as valid the upgraded blocks. But here we require that the upgraded parties do not accept the unupgraded blocks. And so that the unupgraded parties have a motivation to upgrade, since they will see their blocks stay outside the chain. It is generally believed as less dangerous, but we still need the majority of the miners to upgrade in order for it to be a successful update. And now we have the Velvet fork, which was suggested with the Superblock Nipopaus paper. And it's kind of similar to the soft fork case because it is backwards compatible. And again, the protocol changes come as auxiliary data in the block. But here, the protocol changes come as a recommendation, meaning that upgraded players here are required to accept unupgraded blocks. And the most important thing here is that not only do they have to accept unupgraded blocks, but they also have to accept blocks that contain any kind of auxiliary information, even if it is seemingly truthful information, but invalid information. And this is a really important point because this is what the attacker will try to exploit in this Velvet fork condition. And last but not least, Velvet fork suggests that only a minority of miners needs to upgrade, and the protocol should be just fine, actually, so to work efficient enough and secure enough. And since this sounds like magic, but it's actually really dangerous. And let's now step into our contributions. So we have that argument of the original paper of Superblock Nipopaus paper, that Superblock's protocol can be deployed more or less as is under Velvet fork, and it will work secure and efficient enough. But this is not true, and let's see why. As we said, under Velvet fork conditions, the honest parties have to accept any block that contains any auxiliary information, regardless of its validity. So an attacker could here append this black block in the honest chain, which contains false super pointers. And these false super pointers could even point to blocks that belong in a fork chain or in different chain whatsoever. This is what the adversary will try to exploit for the attack we are going to present. Now we are going to call these blocks, these adversarially generated blocks, thorny blocks, because if you see in this example, this extreme case where we have many super pointers that point to blocks of many different fork chains, it resembles thorns of a bush. So we will call them thorny blocks. Now let's see the chain queuing attack that we introduced in this work for the Velvet fork deployment. And so here we have an honest chain CB and an adversarial chain, which is a fork chain of CB CA. And all the black blocks you see in this picture are assumed to be generated by the attacker and contain false superpointers. So what the attacker can do primarily is, let's say, starting from a block A belonging in a fork chain, and he can add a false pointer here to jump onto the honest chain, let's say to a block B, and then follow normally the superpointers of the blocks in the honest chain up to a point that she reaches a block A prime, which is a block she generated in the previous time. And this is a thorny block that points back to the fork chain at a block B prime, and then just follows the path up to the Genesis block to complete a proof that will be sent to the client. So what we see here is that with this false auxiliary data, the attacker can literally cut and paste arbitrarily large portion of the honest chain into her proof. So she can strengthen the proof of work contained in her proofs and have much higher probability to trick the client. And here I'll just show you a more concrete attack of more concrete chain attack, where the attacker aims at a specific level of superblocks. And we have actually simulated this attack and found out that the probability for it to succeed is about 30%. Now, we suggest a patch for the Velvet protocol. And we concluded that the best thing we can do is to actually cut the way for the attacker to perform these jumps from one chain to another. So what we say is that we have to slightly alter the miner's algorithm while constructing a new block. And we say that while the interlink data structure is generated for a new block, meaning the superpointers in the new block, there should be no pointers that point to thorny blocks, to invalid blocks. And this is a way to not let the attacker do this jump from chain to chain. So what happens here now is that the attacker may append some black blocks on the end of her proof, but by the time she adds an honest block in her proof, she cannot append any other block containing invalid pointers in it. So what we have is that the adversarial proofs generally have this form. We can have a thorny suffix, but up to the point that an honest block is put into the proof, we go all the way back to the Genesis block with honest blocks. Because, as we said, there are no superpointers of honest blocks pointing to thorny blocks. And this comes with a cost, of course. And the cost is that honest provers also cannot contain such thorny blocks in their proofs, because honest proofs contain only honest blocks. And this is not as good, because such thorny blocks like A prime do belong to the honest chain and have some representative amount of the hashing power in the honest chain. So we can say that by doing this, the hashing power in the honest chain is somewhat diluted. So now we can think of a combined attack after this protocol patch. And it's an attack that combines suppression and chain chewing. And let's see in short, step by step, this attack. Let's say that the attacker starts by generating a block B as a fork fork block that contains a double spending transaction. And then what she does is that she tries to generate as many thorny blocks as possible in the honest chain. And at the same time, she tries to suppress as many honest super blocks as possible. And she does this in the following way. She mines selfishly these black blocks in the honest chain, and she announces them to the network only when she observes an honestly generated superblock. So she does this again and again and again, and some of her suppression attacks will fail, some of them will succeed. And we see here a case where the suppression attack fails, but the advantage that the attacker has in this case is that the suppression attack may fail, but she can still use the proof of work hashing power contained in this block, because she can always put thorny pointers to the next blocks in the thorny blocks in the honest chain, and then she can construct a valid proof containing all her blocks to persuade the client. And now, because of this combined attack, we have proved that the security assumption we have to make here is that the adversarial hashing power needs to be less than the 1/3 of the hashing power of the upgraded honest miners. And I want to reason about this result a bit, just a high-level intuition. So one could think, in the first place, kind of naively, since we have a situation here that the upgraded honest hashing power competes the adversarial hashing power, why isn't this assumption enough, that the hashing power of the attacker is just less than the honest hashing power? And in this case, because of the suppression attack, you can see that we can have the extreme case that all of the blocks in the honest chain are actually adversarially generated. So the honest players, honest provers cannot compete the adversarial proofs. And now let's see a slightly stricter assumption that says, let's say we have for the honest parties 2/3 of the total hashing power, and the rest of it is the adversarial power. But here we stand right on the borderline, meaning that in the extreme case, we can have that half of the blocks are adversarial generated and the rest of them are honest. So we need something a bit stricter than this. And we prove in the paper that this is the assumption to go forth. Now, let me say just a couple of things about Flagling. And Flagling is another Superlight client protocol, and the consensus protocol changes it requires is that in each block header there is an additional Merkle route, and this is the route of Merkle mountain range chain commitments, and it commits to the whole blockchain history up to this point that this block is generated. So the protocol says that the prover sends a claim for the proof of work, let's say, contained in the chain.
Sorry,
yeah.
Leave it.
Yep.
We're a bit over time. Maybe one more minute.
Yeah, just 1 minute, and I'll be thank you. So we have that. What happens here is a random sampling of few blocks, and then along with Merkle proofs, and the client should verify that these Merkle proofs are all consistent one with another. Well, I will conclude saying that there was again an argument that said that Flagling protocol could be deployed as is under Velvet fork, but we show that in the worst case, that could be again a combined attack, really similar to the one we described before for the PATS protocol of superblocks. And I just want to say that There needs to be some more research on this topic to conclude to the security assumptions that need to be made for the development Flagling Protocol. And this is all for me. Thank you very much for your time.